So let's go over the midterm, what it means. So if you go to the class website, there is a doc file, you can click on it. If you click on this doc file, it has all the links embedded. So first of all, in this doc file and also here, you can see your team assignments. I have randomly split you into teams of 5 or 6. I have given you names from my favorite TV shows. If you don't know what's the pupa, you can go and do a Google search. So you are in teams of 5 or 6, something like that. And you can see which team you are in. It's completely random. I'm not going to change it anymore. So make sure you know. You can see people's name on this and you can contact them on Slack. It's all online. And try to set up your first meeting to talk over how you're going to do it. So this midterm has 4 papers that you need to pick from. The papers are in this Google Drive. The Google Drive has the midterm itself and the 4 papers. And I'm going to talk about the papers briefly in a moment. So what you're going to do is to pick a paper. As a team, you have to decide. So one of you might like paper A, the other one might like paper B. You have to make a convincing case. Don't go for the length of the paper, or just because a paper has fewer equations, that does not mean it's an easier paper. You have to really see what you want to do and take your time first going over all 4 papers and see which one you like. So, and I will talk about the papers in a moment, but what do you do once you have decided the paper? What you're going to do is, there are 2 things you have to do. First, you have to prepare a report. In every team of 5 people or 6, you will have your own individual report. The report will be a product of your discussions and things like that, but it is your own report. I would prefer if your report is typed and you have printed it out, but if you don't have access to a printer, you can just write it down. However, don't write it like this. So it's not clear what you have written, just to squeeze in more information. If I get grumpy, I will deduct points, okay? So don't make me grumpy. If it's typed, then it should be in a normal font size, 10 or 11, something like that. If you want to do 12, that's okay. But this is basically practice for you, for those of you who will be applying for fellowship applications. They will tell you this particular font size, this many pages. Every year, there are some students who, in spite of me saying, do not exceed 2 pages, and I will point blank deduct 25 points. If you exceed 2 pages for whatever reason, I'm going to cut 25 points. This is a 2-page report. You have to write a 2-page report, period. No questions asked. If you think there is more information, try to condense it. Sometimes I have to talk about research done by my whole group, which is 10 PhD students or so, in 2 minutes. I have to talk about everything in 2 minutes. That's what it is. You have to write the report in 2. So decide what do you want to present, what you don't want to present, okay? Make those decisions. In this report, you have to provide your name, the full reference. You can look up what's the meaning of a Chicago reference style. You have to make 1 figure. This is also where students ask questions. A figure does not mean a square box with a bunch of text written inside it. Okay, that's not a figure. You can have some text in it, but it's a schematic that explains the key ideas in it. You can have some equations, you can have some text, but the more pictorial it is, the better it is, okay? And you should have 4 points numbered. So just clear-cut 4 points. What are the key findings of the paper? The key finding could be an equation, it doesn't matter, but again, try, what are the key 4 points? And these are things you will discuss with each other in your team. So, and then 4 points on the tools used in the paper. By tools, it could be equations, theories, concepts that relate to 481. 4 points on what you liked about this paper, and 2 points what you did not like about this paper. Okay, so go at it. Be mean. It's your chance. And I need a statement describing how many meetings. In every report, you should have a statement. How many meetings did you do to discuss the paper? Which members attended which meetings? So this is like an honor code. You have to account for if one member was not attending every meeting, any meeting at all, I will see this, and this will lead me to deduct points. So this is a group activity. I would like to see that you met. That's why you have been divided in basically random teams. So you get to know each other and work on it. So that's 75 points. This is where, and I'm going to be lenient. I want to be lenient. I want you all to get good grades in this class. Okay, I have no, if all of you, like I said in the beginning, I'm not going to be like 1/3 A, 1/3 B, 1/3 C. I don't care about that. If all of you meet a certain threshold that I expect, you will get lots of A's, no problem. So in this exam, it's easy to get full points. Don't screw it up. Don't write a report which is longer than 2 pages. Don't make a figure which is only text. Do the common sense things and enjoy the paper. This part of the class is something every year students seem to love it a lot. Then there is a presentation. It will be a 3-minute presentation, and you will be making the presentation here. So what you're going to do as a team is to work on the presentation together. You will send me the file the night before December 1. December 1 is the presentations will happen. If you cannot make it to class, I understand, but if your full team cannot make it to class, that's really odd behavior, right? So let's make sure that at least half of your team is present or more, and ideally all of you should present. Okay, you can do it. And you will be coming here, you will be making the presentation, you will be getting exactly 3 minutes. If you exceed 3 minutes, I will bring a big stick. I'm gonna like really kick you, and I swear I will bring a stick or a broom or something like that, you know. The presentation will happen from my computer to keep it efficient. So you will send me the file. It should be either a PDF or a PowerPoint. If you have some movies in the file, then you should use a PowerPoint. To send it to me on Slack or by email, I will have it ready on my computer. We have 10 teams, 3 minutes. We leave some time for question and answer. After every presentation, you will be asking the team any questions, okay? And we will also be voting on the funniest or most entertaining presentation, who will get ice cream with me. So that's the second midterm. Any questions about this before I go into the papers? Go ahead. Within these guidelines, you do whatever you want. Okay. So when you write a report, it's your task to make it clear to everyone. So sometimes people submit reports without section headings. Those are hard to read. So I recommend having section headings, but this is something you know, of course, I recommend it. I've not made it a guideline here. Maybe you write a very nice report without section headings. Well, if you can do that, I would be surprised, but that's okay. So it's good to have section headings and decide as a team what section headings should we have. Okay, go ahead.
So like for the 75 part, it says that it's individual, but then it also says like meet with your groups. So what percentage are we allowed to like play off each other versus 1%?
It's up to you.
Okay.
Just don't copy. If I go like, oh, okay, don't copy paste. Okay, and I don't think this will be a problem. Every year I have seen very individual reports, so I'm not worried about it. Okay, any more? There was a question in the back. Okay, let's look at the papers. There are 4 papers. First one is by someone named Charles Bennett. You can go and Google about him. Charles Bennett is considered to be the father of modern quantum teleportation. He came here to give a seminar also. I actually once got to write a computer code for him, which was a lot of fun. So he's not very old, but he used to work at IBM, and he got his PhD in material science, and then he moved into things like quantum mechanics, very heavy duty. So this one talks about Maxwell's demon, which is something that for a long time people used to think violates the second law of thermodynamics. And in this paper, he reconciles the Maxwell's demon with second law of thermodynamics through some ideas, and you will study what those are. The second paper is, Cosmo's gonna like it. It's a geology paper from Earth and Planetary Sciences Letters. What you might not like, it's got a bunch of equations. It uses like all the equations that you have seen here. You see this? It uses a Maxwell relation, for example. And it uses this to talk about what happens inside the core of the Earth. The core of the Earth is primarily made of silicate liquids and other things, and it studies what the problem with core of the Earth is. We cannot go there, right? We cannot, even Elon Musk or all these Richard Branson type people cannot design a rocket that goes to the core of the Earth. It's really hard to get there. So people have to come up with models to explain what's going on. And this is one of those papers. It's an application to geology. The third paper is a biochemistry paper, which I think is super cool. It talks about entropy changes in processes involving proteins. It uses things such as you can see lots of, I think it uses the Gibbs-Helmholtz equation, and it talks about how can you measure the heat capacity of a biomolecular system to talk about what's really going inside that biomolecule. So it's a really nice paper. It's a bit old, but it's really nicely done. The fourth one is a very interesting paper. We have all talked about ideal gases, you know, how things don't talk to each other. So this paper is almost like an ideal gas. It's called hard spheres, you know, things, they have a finite size, but otherwise they don't talk to each other. Turns out, even for these hard spheres, you can get really complicated phase diagrams. This is mole fraction of A, this is mole fraction of B. And depending on the mole fraction, you can get these super complicated phase diagrams. These things are important in self-assembly. So this paper is by Dan Frankel, who is a very famous, he's also, I have his book, and it's a really nice book on doing computer simulations. So these are the 4 papers. Meet as a team, decide which one you want to work on. Okay, and all the instructions are in the file online, including your team assignments. These are all TV shows. If you, you can basically see which TV shows I watch by looking at the team names. Any questions? It's not that complicated. Just meet as a team, go through the papers and work hard, and you will get 100. It's going to be hard for you not to get 100, but that said, every year there are 2 students who get 50. They just don't do it. And I cannot help you if you're not doing the due work. There are few students who will get 75 or 80. Again, don't exceed 2 pages and write a decent report. Just be honest in what you're doing. I don't expect you to understand everything about the paper because it is a research paper. It's a complicated paper, and that's okay. You're not expected to understand everything, but you are expected to understand the big picture and how is PChem helping in it. Okay, any questions? Okay, so let's talk about mixing and solutions. So last time, what did we do? We talked about, oh, and there is no class on 19th November. So next Friday, there is no class. Use that time to set up your first meeting to go through the paper. You know, definitely that is one time that works for everyone. This classroom will be empty. Just come and sit here, work in teams. And if you want to do on Zoom, that's also fine. Whatever you want. So last time we talked about mixing of 2 ideal gases. So we are really talking about solutions at this point, right? What is a solution? A solution, we think about a solution as necessarily being liquid, but a solution is anytime you have a solute and a solvent. You have one species and another species that exist with each other, and that's a solution. So we are talking about the simplest solution we can think of is mixing of 2 ideal gases. And here we derived the expression that the free energy of mixing, which is the final Gibbs energy minus, and this is at constant temperature and pressure. We derived last time that the final minus initial energy is RT XA ln XA plus XP ln XP. From this, we showed that the entropy of mixing is minus R XA ln XA plus XB ln XB. And this immediately, if you get the delta mix H from this, which is delta G minus T delta S, you get that is 0. There is no enthalpy of mixing, right? And we made a plot for this, which the plot looked, so this is XA is equal to 1, and this is XB is equal to 1, XA is equal to 0, XB is equal to 0. We plotted this and we showed that, and this is practice problem 13 or 14, something like that. I have put it in the folder, that delta mixing G is going to look like this. It drops down, it is 0 at both ends, and it drops down with a slope of minus infinity. That's what we showed. And the delta mixing H is going to be uniformly 0. There is no effect. We just showed it is 0. So this is for a mixing of 2 ideal gases. And the delta mixing S is going to be opposite in sign of delta mixing G. Right? This is what we showed for mixing of 2 ideal gases. So let's go. Any questions about this? Go ahead. Huh? Oh yeah. I'll just erase this and you can figure it out. There's nothing profound there. You know what it is. Using G is equal to H minus Ts, right? So you can do that. So let's think about the next more complicated step, which is mixing of A and B again, but this time we don't just have gas, we have A in gas plus liquid form and B also in gas plus liquid form. Okay. This is what we are going to do next. And it's really simple. This is how it's going to look like. Now we have a container. And in this container, we have the liquid in the bottom. We have A liquid plus B liquid. And here we have A gas plus B gas. Okay. And we want to talk about the delta mixing, the mixing Gibbs energy here, the Gibbs free energy of mixing over here, the enthalpy of mixing over here, and all the three things that we did for mixing of two ideal gases, we want to do for mixing of not just gases, but also liquid. So here, once again, we will assume gas is ideal. And this is where it gets a bit funky, because if you really have ideal behavior, what does it even mean to talk about gas and liquid separately? They're kind of same. So it's a bit tricky, but we hopefully it will make sense. So we'll assume that the gas is ideal. And second, we are assuming that gas is in equilibrium with liquid. So here I'm going to give you the expression and the gist of how we get at it. The full thing is done in Atkins. It's just bookkeeping and it gets messy. So like almost everything we are doing in class, there are few things that are not in Atkins, but most of the things I'm doing are closely from Atkins. So I don't remember the section number, but if you go and look up mixing of just ideal mixing, you will find the full thing where he goes through the math. They go through the math very carefully, but I'm going to give you the gist of it. So we have ideal gas is ideal and gas is in equilibrium with liquid. So when the gas is in equilibrium with liquid at constant temperature at pressure, what can we say about the chemical potential here? We can say that the chemical potential of species A in the gas phase must be equal to the chemical potential of species A in the liquid phase, and the chemical potential of species B in the gas phase must be equal to chemical potential of species B in the liquid phase, correct? That's the definition of chemical equilibrium. Note, we are not saying that the chemical potential of A is the same as chemical potential of B. That's not going to happen. They are two different chemicals. Unless they are the same, they won't have the same chemical potential, right? So they might in some freak case, but it's not really true. We are not imposing that. What we are saying is that the chemical potential of A is similar in both phases. Chemical potential of B is similar in both phases. So once we have this, we are really set in using the equations that we just derived for the mixing of two ideal gases. Once you have this, you can completely ignore that you had a liquid existing below this. You can just think about the gas existing at the same time, or you can just completely ignore the gas or think about the liquid existing at the same time, right? So we can just think about this one, A gas and B gas that are in equilibrium with each other with their own chemical potentials. And we derived the mixing free energy for this one, right? That's what we showed last time. So through this, and this is where I'm making the intuitive argument. If you go through Atkins, you will see they go through a lot of math to make this rigorous. You can go through it, but the intuitive idea is what I'm telling you next, or telling you now, that gas and liquid are in equilibrium with each other. So we can directly use the equations that we derived for the gas, for the mixing of ideal gases last time. In other words, we can directly say that the delta mixing G per mole is going to be the same. It's going to be RT XA ln XA plus XP ln XP. So I have done nothing. I've literally copied the expression from last time, from the last page. The idea being that gas and liquid are in chemical equilibrium with each other. So their chemical potentials are the same. If their chemical potentials are the same, whatever we did last time carries over directly. It's a bit of cheating here. If you're very rigorous about this, you will see that you have to account for the algebra correctly. And Atkins does do that, but I'm not going to get into it because every time I do this, it's an hour of just algebra bookkeeping and we lose the big picture. The big picture is you should remember this wonderful equation. Mole fractions of A, mole fraction of B. And this equation applies if you have applicable if only gas A and gas B, also applicable if gas A equilibrium with liquid A and gas B equilibrium with liquid B. Because once we have equilibrium, the chemical potentials are same and we really don't need to worry too much. We can just write it down right away. Okay, but go through Atkins if the algebra here is not, if you're not happy with this argument, go through Atkins, look at the full proof. But remember this equation, okay, which so for ideal gas, it applies to even when you have gas and liquid. So on the basis of this equation, what can we now say about delta mixing H? Can we do the same thing as last time? Go ahead. It's just going to be 0. There is no difference, right? So you can once again see that delta mixing H is equal to 0 and delta mixing S, which is minus partial delta mixing G by partial T at constant P is equal to minus R XA ln XA plus XP ln XP. So we get the same equation once again. And here we have assumed ideal behavior even for the liquid, which means that we are saying that partial pressure, we have assumed in all of this that the partial pressure is equal to mole fraction multiplied by the total pressure. Okay, so if you want to read more on this, go and read the chapter in Atkins, but I'm not going to go too much into this. I want you to remember this expression. When things are ideal, the Gibbs free energy looks like this. The entropy of mixing is the only thing that contributes to the Gibbs free energy. The enthalpy of mixing completely disappears. That's the big picture here. Any questions? Go ahead.
Does this apply to the critical point?
I think so, but you have to be a bit careful because you don't. First of all, ideal gas won't have a critical point. That's the first thing to remember. So no, you have to have a van der Waals gas, so everything breaks. You can come up with similar expressions, but since you can't get critical point for an ideal gas, so this is something to remember. The simplest equation of state that gives a critical point is a van der Waals gas. Ideal gas doesn't give a critical point. So, okay, so we just showed something which is useful for, yeah, go ahead.
What did you say after it says also applicable?
If gas A in equilibrium with liquid A, if gas A, I guess I can. Now it's clear. Good, I'm not going to do that. I will get a fat finger just by typing all day. Okay, so this is all ideal, right? And you will see in one of the papers for this midterm, there are things that can conform to this picture when you have hard spheres that don't talk to each other. Actually, this can be kind of useful for even macromolecules. And that is what leads to this whole field of self-assembly, which is very, very interesting. But things are not talking to each other, yet they assemble in complicated formats. However, most solutions in chemistry are not ideal. Chemicals are talking to each other, right? You have all these complicated interaction when you are putting protein next to another DNA or anything else. You have a surface, everything is talking to everything. So this model is not going to be applicable to really complicated systems. So how do we talk about that? Okay. So in order to talk about that, we have to go to something called a regular solution model. Okay. That's what we are going to do next. So let me make a table which will show how these models work. And we will do regular solution model. There is a model which is even more complicated than this. I will tell you what it is. We won't be doing that one. So in order to do this, we have to think about so let's make a table. In this table, I'm going to have okay. So here, first thing we have is an ideal solution. Then we have a regular solution. And even more than a regular solution, there are real solutions which are even more complicated. So I'm going to tell you how those work, but let me write it down, the key ideas here. So what we want to write in this table is the delta mixing Gibbs energy. Then we also want to talk about the entropy of mixing. And then we want to talk about the enthalpy of mixing. So let's start. For an ideal solution, what is the enthalpy of mixing? 0. I would have expected a bit more enthusiastic sounds, but that's okay. What is the delta mixing of G? We just derived it, right? It is RT XA ln XA plus XB ln XB. And we showed that delta mixing entropy is minus R XA ln XA plus XB ln XB. In a regular solution model, we account for the fact that the enthalpy of mixing is not going to be 0. It's going to be different 0. Oh, sorry. So in a regular solution model, we will account that this is not equal to 0. We will see how much it is. We will come up with, it's going to be what is called a bit phenomenological, which means I'm not going to derive it completely from first principles. I'll give you intuition as to what it might be. This is kept the same as ideal. The entropy of mixing in a regular solution is the same as the entropy of mixing in an ideal solution. What will happen to the delta mixing of G in a regular solution? Will it be the same as an ideal solution? No, it won't be, right? The entropy is same, but you have an enthalpy contribution. So this will be not equal to ideal. In a real solution, once again, the enthalpy of mixing can be non-zero. It will be non-zero. Sometimes it might be 0, but in general, it will be non-zero. The entropy of mixing as well will not be the same as ideal. We let that also change. And this will also not be equal to ideal. So this is the whole hierarchy. A real solution is more complicated. What really happens in real solution is that you start accounting. First, just let's talk about regular solution, and I will show you how you go to real solution. But the regular solution model is really powerful. A lot of chemistry, chemical engineering, material science you can do just by using the regular solution model. It tends to be quite powerful. Even though it assumes such a simple form for the entropy of mixing, it still happens to be quite powerful. So let's work with this regular solution model. How do we work? So regular solution model. And once again, it is mixing of A and B. These could be gases. These could be gases and liquid in equilibrium with each other. As we saw, that doesn't really matter. If you have gas in equilibrium with liquid, the chemical potential is the same, right? So I'm just going to write mixing of A and B. And here, we keep the same delta mixing S as delta mixing S ideal. We don't change that, okay? We just use that. Why do we don't change that? Because, well, it's a model. We are allowed to do whatever we want to do in building this model, right? So this is an assumption of this model. So we know how much this is. This we know is minus R XA ln XA plus XB ln XB. We like this entropy expression so much that we keep it. However, delta mixing H is no longer zero. This accounts for interaction between A and B. So now let's try to be creative and imagine you are all scientists trying to come up with a model for this. So pay attention. What is the simplest model that you can think of which accounts for the interaction between species of type A and between species of type B? I want to write down an expression that depends on the mole fraction of A and depends on the mole fraction of B. What is the simplest expression you can think of over here that depends on both of them? Go ahead. Huh? So why XA multiplied by XB? Why should it not be just XA? It's the interaction, right? So this is the key point. So let's say I'm talking about interaction between all the material science students here and all the chemistry students here, right? So I want a term, if I just had XA plus XB, that means that it would have some contribution if XA was equal to 1 and XB was equal to 0. But that's not mixing, that's just pure A, right? So the simplest expression that you can think of will be a product of XA and XB. You can have more complicated things. Why stop at product? You could have XA square multiplied by XB, right? So regular solution model stops at XA and XB. So you can see the more you have different number of A and B, the higher it's proportional to both A and B. And it has a proportionality constant, which we call omega. Okay, so this omega is known as the regular solution parameter. So what should we do to omega in order to recover the ideal gas mixing? We make it 0, right? If omega is 0, we recover the ideal solution model. And I will give you a little, omega is actually quite physical, that we can get a lot of intuition into what omega might be, and we will talk about that in just a moment. But let's write down the full free energy of mixing for the regular solution model. So regular solution delta mix G can now be written as omega XA XB. So what is delta mix G? It is delta mix H minus T delta mix S, right? And we have S over here. Do I have the right expression for S? I do. So this is going to be plus RT XA ln XA plus XB ln XB. I haven't numbered equations today, so let's call this as equation number 1. And let's call this as equation number 2. So this is the free energy of mixing for a regular solution model. All we did was to keep the same entropy of mixing as the ideal solution. And we said, look, things are not ideal. So if you mix things together, they are going to talk to each other, and there might be some change due to that. Could omega be positive? We said if omega is equal to 0, we recover ideal mixing. Does omega have to be positive always? Does omega have to be negative always? Can it take any sign? Huh? Right? It depends on how A likes B and how A hates B or things like that, right? So omega can be positive or negative. Omega can be positive or negative. So this is where I'm going to deviate just a little bit from Atkins. I think Atkins just calls it a parameter and says, go home. That's not good. There is actually a lot of intuition you can get into omega. And that's what I will tell you next. I won't derive the full thing. The first time I taught PChem, I derived the full thing. And then it was a lot. I mean, there was a math explosion in the class. So I stopped. I won't derive the full thing. So omega is equal to what? So the best way to derive omega is through something called the Braggs-Williams approximation. Does anyone know who was Braggs? Has anyone heard Bragg's name before? Go ahead.
Something with X-ray?
X-ray, but anything else? He won a prize. He won the Nobel Prize. But do you know what's special about his Nobel Prize? He still happens to be the youngest person to have won the Nobel Prize in physics, age 24. I'm way older than that. So Bragg's, and even more interestingly, he won the Nobel Prize with his father. They both, I think it is the only father-son team to have won the Nobel Prize the same year. Won Nobel. So go and tell your dad to stop being lazy, you know? Or your mom. You can tell your parents that you are the reason why my science is stuck. No? Only if you were doing better science, I could be winning Nobel Prize with his dad in around 1930s or so for X-ray diffraction. So Bragg's law is something that allows us to do X-ray diffraction, which is very important. So it's the same Braggs who worked on this, Lawrence Braggs. And I don't know Lawrence, but I don't know whether this is the father or the son. And you can't blame me, right? So Bragg-Williams approximation. So let's talk about omega. Omega is talking about the interaction between A and B. So it comes from the following physical perspective. Let's go back to something really, really fundamental, which is the potential energy curve. Okay, so let's draw 3 potential energy curves. All of these are potential energy curves. So U versus distance between two A atoms. So I'm talking about the potential energy between 2 A atoms. This one is going to be the distance between 2 B atoms. And this third one is going to be the distance between A and B atoms. So we know how a general potential energy curve looks like. Like if it was ideal, it would just be infinite and then down to 0. But we have drawn these curves for real materials, and which we saw that they tend to look something like the sharp. They rise very sharply when you go to 0, and then they gradually go back to 0. Okay, that's a typical curve. So let's say we have 3 different curves. This one is for U between A and A. This one is for between B and B, and this one is for between A and B. So let's draw 3 curves. And notice something that I'm going to do. I made this one slightly deeper than AA, okay? And this third one, I make even higher. I make it like this, okay? So I have made 3 different depths for each of them. And this depth over here I'm going to call epsilon AB. Okay, so let's see. I want to be careful about negative number or positive number. Give me a moment. Okay, we'll work with it systematically. So what physical aspect in chemistry, what term in chemistry do you think can describe this epsilon AB that I drew? In chemistry, we have talked about this thing. You have talked about this thing in your high school chemistry. What is this? What does it correspond to? You have answered many questions. Someone else? Huh? What do you think? Kind of. It begins with a B. 4-letter word that begins with a B, ends with a D. Bond. It's the bond strength, right? When A and B are forming a bond, the deeper it is, the stronger will the bond be, right? They like to hang out even more and more. So in this case, which one is forming the strongest bond? B, right? It has the deepest well, right? So this term corresponds to bond strength. So over here, let's think about the following quantity. Let's think about epsilon AB minus epsilon AA plus epsilon BB divided by 2. So it just looks like I pulled it out of nowhere, but there is something intuitive, hopefully, that I did here. I'm talking, go ahead.
Just a notational question. When you denoted epsilon AB or like graph of epsilon of like the A to A interaction, that's what we define it as?
Huh? What?
So on the graph for like A's interaction with A.
Yeah.
The bond strength is epsilon, the AA or?
Yeah. It's human to make mistakes. So we can think about epsilon AB minus epsilon AA plus epsilon BB by 2. What does this tell us? This is telling us bond between A and B relative to average AA and BB bonds. So let's be a bit careful about the sign convention here, okay? So let's say epsilon AA is the size of this thing. So epsilon AA we are keeping as a positive number, okay? We are not, just let's just be very, very careful. So this is also epsilon BB. So this is the absolute value of this thing, because otherwise that's negative. And this one over here is epsilon AB. So in this case, let's say epsilon AA, let's give it a number. Let's say epsilon AA is equal to 5 kilojoule per mole. Let's give epsilon BB a number. Any ideas? What number should we give it? 8. Let's go deeper. 10. What number should we give to epsilon AB? 2. Let's go with 2. So let's think about AA plus BB. So AA plus BB by 2, how much is that? 7.5. And AB is 2. So this tells us that if you mixed a bunch of A and B, they would rather, the B's would rather form a bond with the B, the A's would rather form a bond with the A, instead of A and B forming a bond with each other. Is that clear to everyone? It's so much deeper to form a bond between B and B, right? You don't want to hang out with the A's. The B's do not want to hang out with the A's. However, this is excluding entropy. There is a certain benefit in mixing things together. That was the entropy thing that we talked about. This is purely energy. So if epsilon AB is smaller than epsilon AA plus epsilon BB by 2, A and A, B and B are preferred. You don't see AB type bonds forming. You will have a system where all the A's hang out in one side, all the B's hang out in one side. You will always have an interface, and you try to really minimize the size between that interface. However, if epsilon AB, if the bond between A and B was much deeper, let's make a very deep bond over here, which goes like, I don't know, something like this. In this case, forming an AB bond is just so much nicer that anytime you mix A and B, excluding entropy, you like to form A and B bond. And I want to emphasize once again, this is purely looking at the potential energy. This would be valid at 0 temperature. At higher temperature, the entropy starts to matter. So, and I will write this in deep green color so you can see what it corresponds to. AB bonds preferred. With this preamble, I can tell you what omega is. So in Bragg-Williams approximation, omega is given by minus epsilon AB plus epsilon AA plus epsilon BB by 2 multiplied by Z. This is the coordination number. This is how many atoms do you like to hang in your vicinity. This is a property of the crystal structure. So different crystal structures will have different properties. So Atkins does not, so this is outside Atkins. Atkins does not go into Bragg-Williams. And if you ask me on Slack, I can give you a full proof, more systematic way of deriving this. But we have a value for omega, for the regular solution parameter, which tells us if you compare the bond strengths of the 3 possible bonds that you can form, AA, BB, and AB, you can get this term coming to the internal energy. However, this thing that I wrote over here that A and B will like to exist with each other, this is completely ignoring the contribution due to entropy, right? We know that entropy always likes to mix things together. So there is a trade-off going on between entropy and enthalpy, depending on the size of omega. If you have AB bonds being preferred, then there is no trade-off. In that case, energy is saying mix, entropy is also saying mix, and everything is wonderful. But if you have a situation where AA bonds are preferred over BB bonds, then you have a competition. And next time we will talk about this. So next time we will use this information and work with this equation. We will not really go into the value of omega. We will just work with whether omega is positive or negative. Just give me a moment and look at free energy curves. Go ahead.
This works for any like mixture of A and B, right? Like the, I guess, the information.
Go ahead. I don't understand. What is it?
Like when you omega coming from assuming that it's not full amounts of A.
No. The mole fraction can be anything. That's the nice thing. Because the mole fraction is accounted here in XA and XB, right? The mole fraction term comes later.
Sorry, I just have a really quick question.
Yeah.
So for the paper,
Mhm.
you mentioned that you want us to label the the individual parts. Like you want us to literally write like number one, like in a paragraph. We're talking about. say,
It's
like,
up to
the
you.
stuff we like.
It's up to you.
Okay.
It's really free. Trust me.
Okay. I was because it said to label, and I wasn't sure if you wanted to literally like number one. This is what we like.
Sure, if you want. It's really free. Trust me. Don't exceed the page size and make sure you address everything. How you address it, you have a lot of freedom.
All right, great.
I mean, if you don't want to make section headings, that's fine, but then your paper might be confusing to read.
Section headings definitely. I was just not sure if you wanted us to make like specify.
You could do that. You could do that.
Okay. Also, I think I never got my homework 3 back. Is there like?
If it's not here, then email Connor and ask him.
Okay.
What's your name?
Francesco.
Francesco. Yeah, email Connor and
I
ask
found the
him.
homework 4, but I
Someone must have taken it. It's graded. So worst case, you will get your how much grade you got.
sure.
If it's lost, I mean,
Honestly,
I'm very
that's-
sorry.
That's the important part.
Yeah, that it's we can. So ask Connor. He will tell you how much he scored.
Okay, thank you. What about the project? Is the figures included in the 2-page count?
Yeah,
Okay.
everything in 2 pages.
Also, for this, like delta H is